Hello, welcome back everybody. Alright, so here we are at the third and final part of this section. And it's going to be a little intense because this has to do with nth roots. So before we go on, let me just remind you what an nth root is. Okay, so if lambda is a complex number, an nth root of lambda is a number, say w, such that w to the n power is equal to lambda. Okay, that's all it is. Okay, so a square root of lambda would be, a solution to w squared equals lambda. Okay, now with square roots, when lambda was real, okay, we would say yes, there are, if lambda was a real positive number, then there were two square roots. And if lambda was negative, then there was just then we said it didn't exist. But then with complex, when you throw in complex numbers, we're going to find out that yes, there are two square roots again, and it's just good. They just involve complex non-real numbers. We can also talk about cube roots. When n equals 3, like the cube root of 8 is equal to 2. But we're going to see that there are other cube roots. Okay, and in general, there are nth roots of lambda. Okay, as long as lambda is not 0. It's just that a lot of them are going to be not real. Okay, so like, for example, if we take, if we wanted to find all the solutions to z to the fourth equals 1, there's actually 4 of them. There's 1 here, I, and negative 1, and negative I. Okay, here they are on the plane. Okay, so there's going to be, four solutions, but at most 2 of them are going to be real. So that's where we're going. So what we want to do is we want to find the nth roots of a non-zero complex number. Okay, and we're going to do that using the trigonometric or exponential form of that number. So if z is a non-zero complex number, we can write it as r times e to the I theta. And then the nth roots of z are precisely the numbers in this form. It's a number where the modulus is the nth root of r, and the argument is theta plus 2 pi k divided by n, where k is just any number between 0 and n minus 1. So we get there are n possible values of k, and we get n different values only for each value of k here. Okay, and this really can be written this way in terms of sine and cosine. We can also write it this way. Okay, so remember, the r is going to be a positive number, so we can talk about the nth root of r. This is just going to be a real positive number. There's no problem here understanding it. And then we just, we get the formula for the argument of the nth roots this way. Now, the reason why this works, and I'll just give you a sketch of the proof. So if w to the n is equal to z, okay, let's say w has this trig form, s e to the I phi. Okay, so we're letting s be the modulus and phi be the argument of w. So if w to the n is equal to z, then w to the n is s to the n times e to the I n theta. We know that from De Moivre's theorem, or by the properties of exponents for complex numbers. So we can divide both sides. We can divide both sides by r, and we can also divide both sides by this power of e, and so we get this expression. And s and r are just positive numbers, so this number is going to be a real positive number, which means that this has to be a real positive number, which means this has to be real and positive, which means that this has to be real and positive. Well, the only way that this number can be, this expression can be real is if this term is 0. And the only way that this could, then that would mean that this has to be positive 1. Okay? So that means that this angle n minus, or theta minus n phi must be either 0 or 0 plus some multiple of 2 pi, or actually the same thing. Alternatively, we can just say it's minus 2 pi k for some integer k. And I put a minus here, you'll see why. Because now we can just multiply both sides by -1, add theta to both sides, divide by n, and there we are. That tells us what phi is. And these are distinct values when k is ranges from 0 to n minus 1 for my mistake. Here we go. Aren't you glad that I watched this video? Okay. Okay, and then also this means that if s to the n divided by r equals 1, that means s to the n equals r. So taking the nth root of both sides, we get this. Okay, so let's put this into action and see how we can find some square roots first of all. Okay, let's see if we wanted to find the square roots, two square roots of I. Okay, now for I, r is going to be 1 and theta is pi over 2. We've already determined that. So the square root of 1, of course, is 1, and theta plus 2 pi k over 2 is going to be pi over 2 plus 2 pi k over 2. Well, this is just pi over 4 plus pi k, and where k equals 0 and 1. Okay, when k equals 0, this is 5 pi over 4, or rather pi over 4, and when k equals 1, this is 5 pi over 4. So the solutions will be e, well, I guess we could say 1e to the pi over 4 I, and 1 times 5 pi over 4 I. And what this is, the first one is just cosine of pi over 4 plus I sine of pi over 4. Okay, which is just the square root of 2 over 2 plus square root of 2 over 2 times I. And the cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. Well, cosine and sine are both negative square root 2 over 2. Okay. So those are actually the two square roots of I, and of course, not surprisingly, one is the opposite of the other. Okay, if you multiply one by -1, you get the other. So it's the same thing with you know, finding the two square roots of a real number. Okay, one is the opposite of the other. Okay, let's do another one. Let's say if we wanted to find the square root of square root of 3 plus I. This in this case, r we already know r is 2, because that's, you know, square root of 3 squared plus 1 squared is the square root of 4, which is 2. And again, here we are in the complex plane. That's this number. So this angle is 30 degrees, or pi over 6. So theta is pi over 6. Okay, so now n is 2, of course, the same as before. And if we take pi over 6 plus 2 pi k and divide that by 2, we get pi over 12 plus pi k. Okay, and so that gives us when k equals 0, when k equals 0 and 1. So when k equals 0, this is pi over 12, and when k equals 1, this is 13 pi over 12. Okay. So our two solutions will be e to the pi over 12. Well, I should still, don't forget, square root of r is 2, so we want to take the square root of 2. So it's square root 2 times e to the pi over 12 I, and also square root of 2 times e to the 13 pi over 12 times I. And what this is the square root of 2 times the cosine of pi over 12 plus I times the sine of pi over 12. And this will be the square root of 2 times the cosine of 13 pi over 12 plus I times the sine 13 pi over 12. Okay? And it's going to turn out that this is going to be the opposite of this, direct opposite of that. Okay. Okay. So so that's how we get that. Now, we're able to find out what the exact value of cosine of pi over 12 is, but we're not going to worry about that right now. We wanted to find the square roots of 2 plus 3i. In this case, we've done well. R is going to be, or the square root of 2 squared plus 3 squared. So this is going to be the square root of 13. And it's 2 again, of course, again. And the here we are. Here's 2, 3. So at this point, this angle has to be the inverse tangent of 3 halves. It's the exact inverse tangent because we're in the first quadrant, so we can say it's going to be the inverse tangent of 3 halves. Okay. So the root solution will be now we take the square root of 13 is, because we want to take the square root of r. Well, this is just going to be the 4th root of 13. Okay, so we take so our answer will be the 4th root of 13 times e, and this is going to be e to the what we want to take theta plus 2 pi k over 2 is going to be the inverse tangent of 3 halves plus 2 pi k over 2. Okay, so we can see that when k equals 0, we just get 1/2 times this. So this will be the inverse tangent of 3 halves divided by 2 times I. And then the other solution would be the 4th root of 13 times e to the tangent, inverse tangent of 3 halves plus pi. When k equals 1, this is just 2's cancel, and we get pi over 2. Or actually we can just, that's not quite right, it's this plus pi. Plus pi. Just rewrite this. All right, and then if we wanted to find the first solution, if you wanted to find the first solution, then this would be the 4th root of 13. So this would be the cosine of the inverse tangent of 3 halves divided by 2 plus I times the sine of the inverse tangent of 3 halves over 2. Okay, and then you take out your calculator, and this turns out to be negative 1 point, actually no, it's positive, sorry, 1.674 plus 0.896i if we round to 3 decimal places. Okay, that's approximately what this will be. And of course, if you want to, then the opposite. If you do the other one, it'll just put a minus sign in front of this, and it turns out that's the other root, the other square root. Okay, so that's with square roots. For cube roots, let's do an example for cube roots. So let's first do the cube root of 8. We know from other classes, one of the cube root of 8, we would say, if I asked you what's the cube root of 8, you would say it's 2, right? 2 to the third is 8. Well, there's actually 2 more. So let's see what they are. So with 8, r is going to be 8, and theta is going to be 0, because, of course, 8 is real, and it's right on the positive real axis. So theta is 0. So, the cube root of r is the cube root of 8, which is 2, and we take theta plus 2 pi k divided by 3. Now theta is 0, so this is 0, 1, 2. So theta, so this is going to give us, when k equals 0, we get 0. When k equals 1, we get 2 pi over 3. And when k equals 2, we get 4 pi over 3. Okay. So the 3 solutions would be 2 times e to the 0 I. The second one would be e to the 2 pi over 3 times I. And then this last one would be e to the 4 pi over 3 times I. So those are the 3 cube roots of 8. Now what is this? Well, the first one, of course, is just 2. Second is going to be 2 times the cosine of 2 pi over 3 plus I times the sine of 2 pi over 3. Okay. And this is actually going to be 2 times, it's negative 1/2 plus the square root of 3 over 2i, which is just negative 1 plus the square root of 3 times I. Okay. And then in a similar calculation, we get 2 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3. So this is 2 times, this will still be negative 1/2, but this now, this will be minus square root 3 over 2i. So this will be negative 1 minus square root 3i. Okay. And it shouldn't be a surprise that these are conjugates. It's going to turn out that whenever a complex number is an nth root, then so is its conjugate. Okay, I'll let you think about that. See why that's true. And then if you really wanted to, you could just go ahead and multiply this number by itself 3 times, and you'll see you'll get 8. Well, it'll be some messy algebra, but you can do it. Okay. So those are the 3 cube roots of 8. Now the cube roots of negative 1 plus I. So let's do that next. So negative 1 plus I is over here in the second quadrant. Okay, we can see that A is 1, B is 1, so remember A is negative 1, B is 1, so R is square root of 2. And this angle is going to be 3 pi over 4, right? You can check. You can see this angle is 135 degrees. Convert. You get theta is 3 pi over 4. So you take 3 pi over 4 plus 2 pi k over 3 where k equals 0, 1, 2. And we get that this is going to be 3 pi over 12. Okay, by the way, okay, this is very interesting. I did this, I did this correctly. I did this incorrectly on my notes. So I'm going to say this is going to be 3 pi over 12 plus 2 pi k over 3. And this, of course, why don't we just make this get a common denominator, and this will be 3 pi over 12 plus, if we multiply and divide by 4, this will be 8 pi k over 12. Okay. All right. So when k equals, and then n is 3. So we need to take the cube root of this. So the cube root of r is the cube root of the square root of 2, and this will turn out that's going to be the 6th root of 2. Okay. So, and when k equals 0, this is just 3 pi over 12, or pi over 4. When k equals 1, this is 11 pi over 12. And when k equals 2, this is going to be 16 plus 3, that's 19 pi over 12. Okay, so the 3 solutions will be the 6th root of 2 times e to the pi over 4i, the 6th root of 2 times e to the 11 pi over 12i, and the 6th root of 2 times e to the 19 pi over 12i. Okay. Yeah. And then if you wanted to, you could write these down as cosine and sine. Again, with this you could probably do, because we know we've memorized the cosine of sine and cosine of pi over 4. These maybe not. So if you want to leave it like this, I completely understand. Okay, so those are the cube roots. And of course, none of these are real, turns out. Okay, the last example, the 5th roots of 1. All right, so 1, that's going to be another easy one to start off with, because here's 1, so r is 1, theta is 0. Okay, that's the easy part. The hard part, the interesting part, comes when because n is equal to 5. So we will take the 5th root of r is the 5th root of 1, which of course is 1. And the theta is 0, so we take 0 plus 2 pi k all over 5, where k equals 0, 1, 2, 3, and 4. So those give us the angles 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, and 8 pi over 5. And so the solutions would be, okay, again, this is just 1, so we can just write this 1 times e to the 0 pi, 1 times e to the 2 pi over 5 times I, and so on. And again, this, of course, is just going to be 1. Okay, we already know that 1 is a 5th root of 1, of course. But then these are going to be the other non-real solutions. Okay, so this, of course, would be, another one would be, this would be cosine of 2 pi over 3. Why did I make this 3 again? I don't know. It should be 5. So there we go. Plus the sine of 2 pi over 5. So that would be the second solution. And again, the 2 pi over 5, we don't know exactly how to do that right now to find the exact value, but so we just leave it like that. And then the others would be the same. Okay, a lot of stuff in this lesson. Just remember, there are nth roots. There are always n nth roots. Most of them will not be real. Okay. And then that's all I have for today. I wish you well. Good luck on the homework and practice, and I'll see you next time.